Okay, everybody, let's continue with the content of M2. For this content or module, we will look at fundamentals of LSI circuits and design. Okay, the fundamentals. So the outline, this is the outline. There's an introduction part, brief introductions to IC technology and CMOS physical structure and circuits, and design methodology and flow, and the most important part, to use MOSFET as switch. Okay, this is the introductions slides. Whereas a course of objective, okay, whereas a course objective, to understand the significance of LSI technology in modern electronics, to expand knowledge of essential electronic concepts that underpin LSI design, including digital logic circuit design. Okay, so and also signal processing. As I mentioned just now, okay, whenever you deal with CMOS inverter, LSI design, or CMOS technology, it's cover everything, including signal processing as well. And then to build skills and knowledge in LSI design, to advance career in future of IC design. Features of LSI on chip. Okay, you can find nowadays we have CPU, GPU, memory, input-output interfaces, all within single die. As given in the introduction part, we have a single die with the wire bonding, and then high-speed processing enable faster data processing for modern applications. What modern applications? Miss Christina, what is modern applications? What do you think about modern application? Can we call the data transmission as modern applications? Because we have 5G, yeah, okay, that is covered in LSI design as well, okay? And we want to know the cost reductions and size reduction. Why we need to know about this? When we want to fabricate, when we want to design digital devices, we are looking for good cost, right? Of course, everybody looking for the cheaper one. But you must know the specification. Is it cheaper but not good? Is it expensive but also not good? So it's come with the data sheets or specifications. So the integrations of multiple functions on single chip reduces the overall size and manufacturing cost of electronics device. For example, if we have multiple module, we just have the interconnect wired from one part to another part. Why don't we put everything on single die? However, there's a complexity in terms of data transmissions, in terms of path lining, pipe lining. That is very detailed about the features of the LSI design on chip. Then, why MOSFET technology? Somewhere in 1947, the inventions of bipolar junction transistor is carried on with the early transistor technology based on semiconductor junctions. But during that day, it's quite bulky. The system is quite bulky. In 1960, introductions of metal oxide semiconductor. This metal oxide semiconductors is working in enhancement mode. So why enhancement mode, or we can call MOSFET? To better control and performance. Want to overcome the issue with bipolar junction transistor. So in 1980s, CMOS technology is like combining PMOS and NMOS. It's like we have PMOS and NMOS. It's combined into CMOS. Combined into CMOS. And continue to that, in 1990s, scaling and high density integration. Advances in fabrication techniques allow for more smaller, more efficient MOSFET. In 2000, there's a technology called FinFET, but MOSFET still in the market. Okay? For some reason, MOSFET still in use. And SOI, multi-gate devices for improved performance, and future trends we don't know yet. Okay, could be quantum mechanic MOSFET. Okay, when the channel length is shrinking. So this is device. What I'm drawing here is NMOS and PMOS. It's combined like one architecture called CMOS. But before we know detail about, we can learn detail about CMOS, we need to know what is PMOS. PMOS, this is the symbol of NMOS. This is a symbol of PMOS. These two are used in schematic level. Okay, when we want to design combinational logic circuits, sequential logic circuits, we will use this symbol. We don't use this cross-section figure. Okay, PMOS is operations to conduct the voltage in low mode, and meanwhile NMOS to conduct the gate voltage in high mode VDD. And both of these NMOS and PMOS for MOSFET is made up from silicon. Can you imagine? From the sand called silicons, and we can make up the N-type regions for source and drains used for pull-up networks in logic circuits. This is the statement for CMOS inverter. Okay, later we want to do an activity for CMOS inverter. And this one is the NMOS operations used for pull-down networks in logic circuits. So when we combine these two, it's come like one structure. This is a cross sections of CMOS. Very interesting, right? Because we see this color. This color represents NMOS divisions. Normally, we use brown color or yellow color to indicate that one is the N plus divisions. And the green color is represent P divisions. And this one is the ender layer to isolate between NMOS and PMOS. Okay, all this we have input, we call it polysilicon gate, okay, to give an inputs to both NMOS and PMOS. So this is the cross sections of CMOS. So in general, all the foundry in the cell design will follow Moore's law. Okay, so we estimate number of die scaling will reduce, okay, throughout the years. Okay, and you can see the linear shape plotted graph of Moore's law in terms of the die scaling or the sizing of MOSFET. So why scaling? Because we want to reduce the cost, but we want a better performance of design. So we can apply different methods like complementary, dynamic ratio, pseudo network, and pass transistor using CMOS technology. So this is how we project in terms of scaling. Okay, in terms of scaling, somewhere in 1947, bring out to 2006, and then look here, the size is shrinking. Okay, it's go down, and then we don't know the future in 2030. But if you know the behavior, we have knowledge in MOSFET and CMOS inverter, so we can predict. So can you imagine a long time ago how it looked like? We don't want to have this kind of device in our PC, right? But nowadays, we can have flash memory. Okay, starting from 2010, Intel come out with Intel Core i7. And nowadays, we have more advancements in website design. So this is Intel and microprocessor, so you can differentiate. Long time ago, we have this kind of architecture, and now this is what we call layout structure. Okay, moving from that, we miniaturize the die or the skill of MOSFET, and also it will impact the total size of die. So it's going down. You can see the size getting smaller. That's why you can have more compact system on chip. So what I want to say about this, in website design or CMOS, we have two types of designing. We can do analog custom design and digital design flow. There's a difference. In analog or custom design flow, we start with schematic, and then we need to understand the spice model or spice simulations, come up with waveform analysis, physical layout, design road check. This is what I call verification. Just now Dr. Nushat saying about that. Want to know more about design verifications? This is what we call design verification. And RC extractions. Okay, of course we have that resistance and capacitance element on chip, and post layout simulation before tape-out process. And when it's come to us, it's ready as one single electronic appliances. Okay, digital design flow. Okay, Dr. Nushat know about Python. Maybe Miss Chong, you also know about Python, right? Python scripting. Okay, we also have one coding called RTL. RTL is what we use in IC design and CMOS technology. And we can synthesize this RTL coding in any EDA tools, okay, like digital tools, and do the RTL simulation before we deploy it on FPGA. Quite interesting, right? From here, you also can fabricate chip, and you can also test the RTL scripting on FPGA board. So we can have standard cell library, because when we test with the FPGA, there's a standard cell library for the FPGA. Okay, let's look this activity. Okay, everybody, I want you to give your thoughts, what you understand for the past few minutes ago, okay, about MOSFET and CMOS technology. And can you click the link below? I think everybody have the handout for this ready. And create a post with your thoughts, ideas, and any question you may have. Engage with your classmates, the other participants, by commenting on their post. Okay, let's have a look on that. Okay, Dr. Nushat, can you access it? Exactly. Okay, just give any thoughts. You just can write anything that you think about CMOS, inverter, and MOSFET. Okay, everybody can access that?
Yes.
Let's. Oh, okay, great.
Okay.
How about you, Miss Christina? Also can? Okay. Throw your idea, throw what you think in your mind about the differences, and what about MOSFET and CMOS technology. Don't worry, we don't looking for the technical, more technical. Everybody is still learning. You have like 5 minutes maximum. Okay, time to write anything that you have in your mind about MOSFET and CMOS technology. You can describe your thoughts. You can describe the future about MOSFET. Okay, why we learn about MOSFET and CMOS inverter, and also CMOS technology. Any problem?
Just permission issue. This allow more access. And we are looking
How about the other participants? Can you access that list? Okay, Dr. Nushat.
So there, if I don't see any block here, the permissions please.
Oh, alright. No, don't worry about that. You just pause it.
Okay. So this thing is not allowed.
Oh, this thing not allow for you.
So I need to check the cookies.
Mm-hmm. Yes.
Okay. Then permissions allowed. So
Let's see.
yes, this is allowed. So still is not.
Okay, no worry about that, Dr. Nushat. You just can verbally mention it to us about what do you understand about MOSFET and CMOS technology since the training started today.
Okay.
Okay. So let's see how about the others.
I try here.
Okay, don't worry. Take your time. Okay. I want to have your thoughts and what you describe about it. So I know how can I conduct this training in more effective way. So you will learn in 2 days. At least you gain more than 70% improvement than your previous knowledge in the site design. Okay, meanwhile waiting for Dr. Nushat to join us. So I will read through what okay, MOSFET is a type of transistor that is important in digital and analog circuit because it acts like a switch. Okay, great. So you understand the behavior of transistor, right? CMOS is the combinations between NMOS and PMOS to make a logic gates and circuits. Okay, used in most of IC design and microprocessor. Great. Okay, very excellent participant today. There are 2 types of MOSFET, one NMOS and another one is PMOS. Both are having different structure. Okay, having different structure, and it can be used in digital circuits and analog circuits. Okay, great. MOSFET is type of transistor used as a switch or amplified electric signal. Wow, interesting. You know both. One as a switch, one as a amplifier. Okay, that's why we have analog and digital design. So you can within few minutes. Okay, for the first day, everybody can have the big view about MOSFET. It's very interesting. Okay, how about you, Dr. Nushat? Maybe you just can
I
elaborate.
just post now.
You're posting us?
Yes.
Okay, great. Okay, see what Dr. Nushat saying about it. MOSFET can act as a switches, cutoff, saturation modes, or amplifiers. Really, you understand it very well, Dr. Zasad. Depending on the applied voltages and the resulting channel formation. Yeah, very good. I'm happy everybody can gather the information clearly, okay, for the past few hours ago and until now. Okay, let me say about your talks. I'm happy because your talks give some perspective in terms of new tactics, okay, in the medium and for the future. So it looks like we can move on to another topics in this training. Okay, thank you. So let's move on to another topic. So everybody have read the thoughts and share the ideas. And in case you have questions, you want to know more about it, about MOSFET, or you want to wait for the next slide. Okay, let's move on to the next slide. Okay, why FinFET? As I mentioned earlier in this training, instead of using MOSFET, we want to overcome some limitation with MOSFET, but MOSFET still in use. However, for some applications, FinFET is also demanding. So, good on MOSFET nearing limits. So, this statement say good, nearing limits. We don't know after 2030, year 2030, what happened to MOSFET design. So, that is the introductions of using FinFET. FinFET is pretty similar like MOSFET, but the added fin. We add fin structure to the original MOSFET structure that is called FinFET. FinFET can control more higher VT, threshold voltage, VDD and power consumptions. So we can avoid overheating, leakage current. So this is the introduction, why the introductions of FinFET. And one way to eliminate silicon far from gate with thin body. This is thin body from one side called FinFET. However, for this training, I will focus more on MOSFET. But I want you to know there's another options available nowadays called FinFET. But MOSFET is not dying. MOSFET still in use. When you know the behavior of MOSFET, so you can apply behavior of MOSFET to FinFET. Okay, that is the advantage of knowing about MOSFET. So FinFET, this is the cross section. So you can see side by side, this is planar MOSFET. We don't have this dotted line that represent FinFET. So it's pretty similar, right? Look like, but FinFET has this fin. Just to overcome some limitations with MOSFET. So now let's discuss. Okay, let's discuss the differences between MOSFET and FinFET. Okay, Christina, if you are the engineer, you are designing for the first time, and your company asking you to choose whether MOSFET or FinFET. Yeah, for the future. Which one you choose? For the first time design is MOSFET, because MOSFET has the fundamental behavior that apply to FinFET. FinFET apply the behavior from MOSFET. Okay. What is the characteristics on each technology? Can we use the same technology? Let's say MOSFET use 250 nanometer technology. Can FinFET use 250 nanometer technology? How about you, Miss Chong?
I remember FinFET used the technology below 220 and
Yes, because it can work in smaller channel length. That's why it called as a rescue to MOSFET limitation. But if you are planning to design something like amplifier, analog circuits, normally we start with MOSFET. Okay, FinFET is good, but more design on digital. Okay, more design on digital.
more complex.
More complex. Because when we want to avoid the power consumptions, the timing problem, the issue with threshold voltage, okay? Because we want to conduct the MOSFET in terms of three conditions: triode region, linear regions. I mean linear regions, saturation regions, and also pinch off saturation, velocity saturations. It will be complex when you have more complexity on chip. So better switch to FinFET. But the understanding of MOSFET, I could say, very important. Okay, what is the structure of FinFETs that influence the performance? Just now we have just look at the structure. What is structure? What is the added structure to MOSFET? What is the added structure to MOSFET that realized as FinFET? Thin body called fin, right? Thin body called fin. Okay. In which application do you think each one is most effective? Maybe Miss Chong has an idea because she read a lot about FinFET.
The key can be applied in some application like advanced broker, and also it can be applied in the digital signal processing
Is it for FinFET or MOSFET?
for MOSFET.
MOSFET. Okay. Since FinFET is to overcome, it also can be used for the same application of MOSFET, but with better performance compared to MOSFET, because the channel length is less than 220, right? 120, 180 nanometer. Okay, next, let's look what we have for the next part. We will cover on MOSFET in CMOS circuit design. Here you will learn in this training on how to design. Okay, how to come up with linear region, saturation region, and also cutoff region. In saturation region, we have two parts of saturation region. One pinch off saturation and another one velocity saturations, when the size of channel length is shrinking. So let me elaborate the outline. So the first part, we will learn the structure of MOSFET, and then we'll recap what you know about NMOS and PMOS. And then here is interesting IV characteristics on how to categorize NMOS and PMOS. And then the information is about capacitance. Remember, RC element, resistance, capacitance. And then little bits about FinFET. Okay, FinFET analysis. This is MOSFET. It's a major carrier device. This is the floor plan of MOSFET architecture, where we have source, gate, and drain. Look at these two, W and L. This is the crucial part in MOSFET. These two will impact the design performance in terms of IV characteristics and switching. So, this is called channel length, and this one called the width size. So, we need to size the width, then we can have different currents. But before we declare about the width size, there's some voltage needs to power up MOSFET. Everything we do with MOSFET, we need to power up MOSFET. So it can move from cut-off to linear regions and later go to saturation regions. So we will see that here. This is a cross sections. Okay, normally this represent the divisions, and this is the silicon oxide to isolate, okay, between drain and source. Source and drain terminal specified by the operation region. So we will introduce voltage at the gate and the drain. So we can find the RV characteristics. So this is the more close up on the cross sections. So channel length, so the current will flow, the electron movement between source and drain. For this kind of cross sections, there's no current, only MOSFET by itself. Okay, so later we will apply the dimensions on how we can size the MOSFET. So there's a donors and acceptors to create the P area and N area. This is important. We use 0.25 micrometer for this training, but you can apply this basic information for future carrier. So for this training, we use VT 0.43. It's actually associated with 0.25 micrometer CMOS process. This is the symbol of 3 terminal. This is a symbol of 4 terminal. Whenever you do a design, like as an engineer, you will see this kind of symbol. And there's operations. Whenever the gate voltage at 0, so the threshold voltage as the indicator. When the gate voltage greater than VT, then it will turn on. So it looks like a resistor connection there. But whenever VG is smaller than the threshold voltage, it will be in off mode. So there's no current conductions during that time. Okay, this is the basic information of MOSFET operations. So, what threshold voltage? Threshold voltage control whether it's working in cut-off or in linear. It started from linear. If it get greater than VT, when the VGS greater than VT is, then it's turned on. Then you can see the movement of current conductions from linear to saturations. Depends on how much you apply to the gate voltage. So basically, this is the SPICE equations on how we can find out the threshold voltage. But for this training, we will apply the information from the SPICE model and then do the analysis for the MOSFET. So we ignore the body effect for some reason sometimes, but body effect is important if we have transistor network in series. It will cause some body effect that will also influence the current. Oxide thickness. This is what I mentioned with the device level. Okay, before we come up with MOSFET, there is oxide thickness together in SPICE model. So we can estimate what would be the oxide capacitance. Alright. So for the effect, it will affect the threshold voltage. Okay, so it will increase the threshold voltage. It is at 0.43. When we come to the analysis, we will learn further about this. Alright, so this is the example. If we have source buck, if the buck voltage is given as -1 for NMOS, so the source buck you will get 1 volt. So this will affect the total threshold value. Instead of the 0, threshold voltage at 0, so the threshold voltage is increased up to 0.63. Then why? We need to know about threshold voltage. It will influence the current. Okay, look how the current flow from one side to another side. We apply the voltage there, and then another drain and source voltage. So normally we will apply these equations to determine whether it's working in saturation region or linear region. So let's look on these equations. We have two types of MOSFET, one for long channel, another one for short channel. So for the long channel, we will use these equations to design MOSFET in terms of current voltage characteristics. Okay, so this is linear region. Small VDS, if this VDS smaller compared to VGS and VGS minus VT and VDS saturations, then this is working in linear region. So what I can say, VDS smaller than VGS minus VT, then it's working in linear region. So let's look at this example. We use generic 0.5 micrometer. So this is the general equations, because we want it to be in saturation point, saturation region. So apply this equation. This equation is for saturation mode. So given the size W/L, then we substitute this value into this equation, and then we get the current at 93 microampere. But look here, this is the transconductance. Transconductance is very important. Transconductance between NMOS and NMOS are different. Okay, not similar. Because PMOS normally has smaller transconductance compared to NMOS. That's why in CMOS inverter ladder, in this training, you will see double size of NMOS. Okay. So transistor in saturations, when the distance X reaches this point, then it will slowly saturate there until it stops flowing the current. Okay, current will stop flowing. So at this condition we call saturation region. Just now there's no pinch off. There's no conduction there. It's just a very thick layer called linear. And later it's become smaller and shrinking until it's become pinch off. So now we call it saturation mode. So for long channel we apply these equations, and we also have channel length modulations. Channel length modulations due to MOSFET behavior. When we apply more voltage, and it will affect the total current. So you can see VGS influence the current value. When you give smaller current, it at this level, right? If you give more, come to more currents developed operated. Okay, now I want to say about why we learn about VGS. VGS is to control. Okay, VGS is to control the currents flow in MOSFET. I think we move on to another slide, right? So I will continue with short channel and we do another activity, okay, to make sure every participant understand on how to design MOSFET and you can apply in your career path. Okay,